All right. So before we start with today's lecture, I've received a couple of emails asking about the date of exam one, which I believe currently is the Friday after we get back from the holiday break. Would it mess up anybody's schedule if we moved it to the following Monday?
Yes.
Yes? Okay, so leave it alone. All right, it's left alone then. All righty. So today we're going to talk about the small signal diode model because we covered all of the large signal models in class on Wednesday. So as an introduction, we are going to consider a circuit. So this circuit is a odd way, but it would work, to design a voltage regulator. Actually, let me put this down here. So we have some source voltage Vs that we are attempting to regulate. I'm going to have a 200 ohm resistor here. And then I'm going to have a series combination of 5 diodes. Realistically, we would probably do this with a single Zener diode as opposed to 5 normal diodes in series, but there's nothing wrong with this. Where I'm going to define the voltage drop across a single one of these diodes is VD, and because all of our diodes are going to be identical, they'll all have that same voltage drop VD across them. The current flowing down through this leg of the circuit is going to be ID, and for now, we are going to consider our output voltage to be an open circuited voltage like so. So let's say, to start things off, that Vs, our source voltage here, is 10 volts, and our diode saturation current is 10 times 10 to the negative 15 amps. We should be able to see pretty easily that our diode current is going to be 10 volts minus 5 VD divided by 200 ohms, and this will be equal to IS times the exponential of VD over VT, which we can solve using our numerical solver on our calculator to find that VD comes out to be 748.072 millivolts. And from this, our output voltage, which is nothing more than 5 times VD, is 3.74 volts. So we have a simple voltage regulator circuit here where we're trying to make really, I don't want to say any source voltage Vs give us an output voltage of something around 3.74 volts. But what we're going to do now is we are going to perturb this system to see what happens when we make changes. And we are going to perturb the system in a very large, yes. Because there are 5 diodes in series, and they all have a voltage drop of VD across them, so 5 times VD is 5 VD. James. I will discuss it. So what do you mean by the diodes have a resistance?
Well, remember that here, so, all the-
So for metal semiconductor junctions, we had an equation for resistance effectively for ohmic contact, but these are rectifying contacts. So the reason why I'm being elusive is because we're literally going to talk about diode resistance here in a moment, but it's not a large signal quantity, and we are dealing with a large signal circuit. So resistance, a little bit of an aside type thing here, implies a linear relationship between voltage and current. And for a diode, we know that it's largely an exponential relationship between voltage and current. So resistance wouldn't really be the right thing to use when we're talking about a diode. And it's because the slope of that curve is not a constant thing. So the resistance is going to change depending on where we're at along that exponential curve. We'll talk about linearizing that relationship here in just a couple of minutes. So, all right. So what would happen if we change the power supply voltage by increasing it by 10%? Okay, so let's say if Vs increases by 10%, what change in the output voltage occurs? Okay. So this should be fairly easy to figure out because all we need to do is replace this 10 volts right here with 11 volts, right? Everything else is literally the exact same. So we would have 11 volts minus 5 VD divided by 200 ohms is equal to IS times the exponential of VD over VT. Solving for this, we could say that VD is now 751.857 millivolts, meaning that our diode voltage has experienced a change, delta VD, of 3.785 millivolts, and V out, just 5 VD, will be increased to 3.759 volts. And so our change in V out is about 19 millivolts, or 0.5%. Where my change I'm here measuring here is just this voltage minus this voltage divided by the original voltage. Yeah.
Is that 10% to that 0.5%, that a relationship? Or is that?
That's for this particular circuit with this particular value of IS, etc. Let me. Yeah, so the thermal voltage is not expected to increase or anything like that, so we're still using 26 millivolts for VT. All that kind of Absolutely. All right, so a positive increase in our supply voltage yields a positive 10% increase in our supply voltage yielded a 0.5% increase in our output voltage. Now let's perturb the system in the other direction. Let's say that we reduced our supply voltage by 10%. Okay. So same relationships, except we're going to replace that 10 volts with 9 volts. So we'd have 9 volts minus 5 VD over 200 ohms is equal to IS times the exponential of VD over VT. Solving this system, we get VD is equal to 743.655 millivolts. And so our diode voltage changed by negative 4.417 millivolts. And our new output voltage will be 3.718 volts. And so our output voltage change, V out, is negative 22 millivolts, or a reduction by 0.6%. So one thing that we can observe here is that an increase in 10%, increase in our supply voltage by 10% caused an increase in our diode voltage by 3.785. A decrease caused a decrease by a different amount. So we don't have a linear relationship. Getting back to what I was going for before. But we can see that this perturbation once again yielded a very small change in our output of the system. So let's make a different change. Let's say that we loaded this circuit. So instead of having an open circuit as our output, let's throw a 1 kilo ohm resistor in there, because that's definitely a change to our circuit overall. So it counts as a perturbation as well. So I'm going to throw a 1 kilo ohm resistor here. And our output voltage is now going to be the voltage drop across our 1 kilo ohm resistor. That's going to change our equation a little bit, right? So think about things here. Effectively, we're going to have another current, a resistor current over here on the right, that's going to be 5 VD divided by 1 kilo ohm that we need to take into account. So applying Kirchhoff's current law at this node is going to give us the relationship. Let me write this down. What happens to V out if an RL is equal to 1 kilo ohm load resistance is placed across the output terminals here. So my KCL equation is going to look like this. So I'm going to have 10 volts minus 5 VD over 200 ohms. So that's the current flowing in from my supply source, will be equal to ID, which is IS times exponential of VD over VT, plus that resistor current, which is 5 VD over 1 kilo ohm using Ohm's law. Solving for our diode voltage VD, we get 744.854 millivolts, or a change in diode voltage of negative 3.218 millivolts. And our new V out comes to be 3.724 volts. So our change in our system output voltage, negative 16 millivolts or negative 0.4%. Well, like I said, that's a pretty significant change we've made to the circuit, in as much as our load resistance was infinitely large. Now it's a 1 kilo ohm resistor, and we see that our output voltage only changed by negative 0.4%. So this circuit is a pretty darn stable voltage regulator. Okay? So why is it so stable? So it's so stable because our perturbation is only causing a very small change in the DC operating point of each individual diode, right? So if we were to plot our diode current versus diode voltage, we would have a relationship like this. So here's VD, here's ID, and then here we have our exponentially increasing curve. And then this point right here is what's called our Q point, or our quiescent operating point. Right? And so we saw that for a small change in our diode voltage, we really got a small change in our diode current as well. So effectively, if we look at the tangent line of this curve, around this operating point, it'll have a linear slope. We're going to use this linear slope to develop a small signal model for our diode that tells us how it behaves when it's perturbed. Okay? So if the perturbations for our diode voltage are small, then we can say that the derivative of our diode current with respect to our diode voltage is going to be the derivative of IS times the exponential of VD over VT minus 1, which is the derivative with respect to VD of IS exponential VD over VT minus IS, or the derivative of IS times exponential of VD over VT. Close that off, minus the derivative with respect to VD of IS. We know that this term is 0 because we're just taking the derivative of a constant. And so what we're going to be left with is IS divided by VT times the exponential of VD over VT. And this is approximately equal to ID over VT. Yes, James. So this is another reason it tells us why we don't really have to care about the -1. I'm just being more formal about things here. But when we wind up taking the derivatives, it's going to go away anyway. Would not including the -1 literally change the output of this relationship at all? Nope. So, yeah. All right, so we are going to define the dynamic resistance of a diode, lowercase r sub d, as the derivative of our diode current with respect to our diode voltage. And we're going to take the reciprocal of that because resistance should be change in voltage over change in current. And we did everything with change in current over change in voltage. And so that's just going to be whatever our thermal voltage is, usually 26 millivolts, divided by our diode current. And so this dynamic resistance RD represents how the diode responds to small changes in its quiescent operating point. Oh yeah, definitely shouldn't be the derivative of ID over ID because that doesn't make any damn sense. Thank you. Thank you for that, Brody. So let's put this small signal model to use. So in our original circuit, we had this, right? So we had our source voltage, which was 10 volts. 200 ohm resistor. Five diodes in series, like so. Here was our output voltage. Voltage drop across one diode was VD. The current flowing through all of the diodes connected in series was ID. And we perturbed our source voltage by plus or minus 10%. So let's say here that VS is 10 volts plus or minus 1 volt, where this bit right here is our Q point level. And this bit right here is our perturbation. IS was given to be 10 times 10 to the negative 15 amps. And we found that the diode voltage at our quiescent operating point was 748.072 millivolts. That's what we found earlier. I'm just literally taking that number. From this, we can see that our diode current at the quiescent operating point is going to be IS times the exponential of VDQ over VT. And this comes out to be 31.298 milliamps. And from this, our dynamic resistance at this operating point is 0.831 ohms. So now let's see how good of a job our system does at predicting the behavior for this perturbation. Yes. Perturbation. Yes. PERTURBation. Perturbation. All right, so in a small signal circuit, we are going to turn off any large signal voltages and currents because we're only trying to find the influence of the perturbation. So I'm going to turn off this 10-volt voltage source, short circuit it, and in its stead, I'm going to place a 1-volt source that is the perturbation. So effectively, we're treating it like if we had this 10-volt source in series with a small signal voltage source, when we're going to do our small signal analysis, we turn off the large signal source. This is something that we're going to do a whole heck of a lot in this class when we get to our transistor circuit. Okay. So our small signal circuit is going to be this guy. Here we have our plus or minus 1-volt voltage source. We have our 200 ohm resistor. And then we're going to replace our diodes with its dynamic resistance. Because we had 5 diodes in series, I'm just going to call this 5 lowercase rd. Okay. And then the voltage that we measure across this resistance is actually going to be the change in V out due to the perturbation. So how am I going to analyze this circuit? Why is it taking you so long to realize that's a voltage divider? Right? That's way easier to look at than our diode circuit because we no longer have nonlinear relationships or anything that we have to worry about. Okay? So our output voltage should just be plus or minus 1 volt times 5 RD over 200 plus 5 RD. And this comes out to be plus or minus 20.345 millivolts. How close is this to what we got looking at the large signal model? So let's scroll up here. So when we perturbed our voltage source by positive 10%, we saw a change in the output voltage of 19 millivolts. We just got 20 millivolts and change if I'm memory serving me correctly. So pretty close there. When we perturbed by negative 10%, we had negative 22 millivolts. It's still pretty darn close to the negative 20 point blah, blah, blah millivolts we got. So this is a pretty good approximation, right? Without having to go through all of the difficulty of dealing with the numerical solver and all that kind of stuff over and over and over again to see what happens with every single change we make, right? So what change in output voltage would we see if we include a load resistance of 1 kilo ohm and a power supply variation of plus or minus 1 volt, right? So now we're combining all of those effects to see what kind of change we would see, right? So our small signal circuit would be something like this, where we have plus or minus 1 volt. Here's our 200 ohm resistor, our 5 RD, our 1 kilo ohm load resistor is in the circuit. Here's our variation in output voltage. And once again, we just have a simple voltage divider network. But now we're finding the voltage drop across 5 RD in parallel with 1 kilo ohm. And so delta V out will wind up being plus or minus 1 volt times 5 RD in parallel with 1 kilo ohm over 200 plus 5 RD in parallel with 1 kilo ohm. I want you guys to calculate this so that you believe I'm not plugging numbers or anything. Scrolling up just to show you that RD is 0.831 ohms for your calculations. Yes. No, IS is the saturation current for the diode. Yep. So what did you guys get? 20.27? Okay. So incredibly close to what we got without that load resistance here at all, right? So a change of a whopping 75 microvolts is not going to make any appreciable difference on the output of our voltage regulator at all, not even a little, right? Realistically, we could have ignored this 1 kilo ohm resistor. Why? I have 1 kilo ohm right here. This is 1,000 ohms. It's 5 times RD, about 4 ohms. What happens when I have something really large in parallel with something really small? It looks like there's something really small. So as long as we're loading this thing with something that isn't the same order of magnitude as our dynamic diode resistance, it's not going to have any significant impact whatsoever on our circuit. So this is our small signal diode model, how we apply it, all of that kind of good stuff. Anybody have any questions about this before we move on to diode application? All right, yes. But realistically, we're not going to load things that low. So I mean, for a kind of think here, so on, let me scroll back up here. So we have this exponential relationship between current and voltage for our diode, right? So the steeper that we get, or the further along the forward bias curve we get, the resistance is going to be larger or smaller. So if I over V is large, V over I is small, which means the resistance is small, right? So the only time we're ever going to see a diode dynamic resistance being large is if we're somewhere over here in this portion of its curve, which really means that we're not trying to forward bias our diode or anything. So realistically, unless we're seeing like very, very large supply ripples or something like that, we're always going to be operating somewhere in this region where the dynamic resistance is very, very small. And so it wouldn't make, like, we don't have access to some high on resistance and things, right? So any load that we might be trying to connect to our voltage regulator is usually going to have a pretty large impedance. All right. Diode applications. So one place in which diodes are very widely used is a rectifier circuit. So I'm going to draw a diagram here. So let's say that we have some time varying voltage VAC. And then here we're going to have a transformer. Let's make it an ideal transformer just for the sake of argument. Like so. Here's N1, here's N2. And typically speaking, this would be a step-down transformer. So this might be represented with 120 volts RMS. And then across here, this might be 12 volts RMS, something like that. We would feed the output of our transformer into a diode rectifier circuit, which will be this block for now. The output of our diode rectifier circuit would be fed into filter. And then the output of our filter might be fed into a voltage regulator. Such that the output of this system as a whole would be some DC voltage. So if we were to look at kind of a signal flow diagram type thing, we might have something like this. So for this first stage, we would expect to see a very large AC voltage. On the other side of the transformer, we expect a significantly smaller AC voltage. Through our rectifier circuit, and this waveform is actually going to change depending on if we have a half-wave rectifier, full-wave rectifier, etc. We might have something like this, where we're just going to keep the positive portions of the waveform if we're dealing with a full-wave rectifier. After filtering, we might have something like this, where we have approximately DC, but with some ripple on top of it. And then at the output of our voltage regulator, it's now just a flat DC voltage. Right? So we have our AC time varying signal, our step down AC voltage, then here in the middle, our rectified voltage, our filtered voltage, and then our regulated voltage at our output. Those little white blocks that no longer come with our iPhones because Apple are a bunch of cheap assholes do practically all of this. Right? So let's look at half-wave rectifiers first. So we're going to focus today on rectification, get as far as we can, and then we'll talk about other applications on Monday. So a half-wave rectifier is just a specialized type of clipping circuit. And a clipping circuit is just one that clips portion of our waveform so that we keep the part we want, throw away the part that we don't. Okay? A half-wave rectifier, only the positive or negative half cycle of the input signal will actually get sent to the output. Okay? So we have two different half-wave rectifiers that we might see. Very similar circuits. So we have some diode D, some resistance R. Our input signal Vn of T is here. Our output signal V out of T will be measured here. So this is a positive rectifier. So we look at this as a function of time. I'm going to do my input signal in blue. So something like this. And my output signal, if my thing will change colors, will be in red. Don't know why it's lagging so much. Wasn't a moment ago. Something like this, where this value is the peak value of our input signal. And this value right here is VP minus VD on. So we're going to be using effectively the constant voltage drop model for these things to make our lives a little bit easier. If we were to plot our output voltage as a function of input voltage, it might look something like this. So here's the out on this axis. Here's VN on this axis. And this point right here will be VD on. So we would see no output voltage whatsoever while our input voltage is below VD on. And then after we hit VD on, our output voltage should increase with a slope of 1. So it's going to follow our positive input voltage, but it's always going to be a little bit less because of the on voltage of the diode itself. Okay. So we can say that V out as a function of time. Actually, that's not true. V out, let's just call it V out, not worry about the time thing here. It's really going to be a function of V in, but we'll see that in a moment. Is going to be 0 volts for V in less than VD on. And our output will be V in minus VD on for V in greater than or equal to VD on. On the right-hand side of the page, now we're going to talk about our other half-wave rectifier, which is just a negative half-wave rectifier. What modification do you think I'm going to have to make to my circuit to pass the negative portion of my wave shape? Literally turn the diode around. Absolutely right. Here's our diode. Here's our resistor. Here's our input voltage and our output voltage. Plotting things, we'll have something like this. We might stop with half-wave rectifiers for today because I'm getting frustrated with my computer and the lag that I'm getting because it's taking me 3 minutes to draw a straight line. So our input signal will once again be in blue. Something like this. Now our output is going to look like this guy. Draw the line. Okay. Where this value is negative V peak. And then this value right here is negative V peak plus VD on. And then plotting things, come on, computer. Go and stop looking weird. There we go. We might have something that looks like this. Out. Oh, sorry, that's supposed to be VN. This is going to take a minute. I'm not trying to erase anything. V in, V out. Here's negative VD on. And so we should see a line with a slope of 1 here. And then effectively our diode turns off. Like so. And therefore, V out will be equal to 0 volts for V in greater than negative VD on, and it'll be VN plus VD on for VN less than or equal to negative VD on. All right, my computer is annoying me, so this will be a good stopping point. We'll talk about half-wave rectifier applications on Monday, and then full-wave rectification, bridge rectifiers, and then using diodes, logic circuits on Monday.